Okay, so let me have the speaker view. Yeah. Okay, great. So previously we studied the dispersion and nonlinearity, right? We learned that how dispersion and nonlinearity play a role in the pulse propagation, right? In dispersion, it actually changed the phase. It adds the phase in the spectrum domain because different frequency you add different frequency you add different phase, right? So different phase added on different frequency component. So you in frequency domain, you need to add exponential I k naught double prime over 2 omega square z, right? But in the nonlinearity, we add the phase in the time domain, right? We add the phase time domain because it changed the high intensity pulse, changed the refractive index, right? So in the time domain, we add exponential I gamma u absolute value square, right? Times the distance L. So they actually play a different role in the pulse propagation. It could be applied in the pulse propagation in the optical fiber. It could be propagated in the optical waveguide, right? So this is the basic, very basic electromagnetic wave propagating in the optical fiber, in the optical waveguide, right? So now we have the following material. We will learn what is the waveguide, right? What is the waveguide? What's the fundamental structure? How light can propagate? How electromagnetic wave can propagate in this in the waveguide? So the most fundamental waveguide is called SlabWaveguide. SlabWaveguide. So there are actually plenty of type of waveguide. This slab waveguide is the most simple, most straightforward waveguide. One can solve it and express and solve it and find the solution, as using the analytical expression. So here's the first. We'll learn the fundamental symmetric slab waveguide. Symmetric slab waveguide, right? So we have the we have the permittivity epsilon 1, epsilon 2, and the epsilon 1, right? So x is d over 2, x is negative d over 2, right? So this would be 0. So the width of the slab is d. So thinking about this, just imagine this is slab. It goes to infinite, out of the whiteboard and goes to infinite into this whiteboard, left and right, right, left and right. So it's a slab. So let's have the dimension. So this is the z, x, x, y, z, right? So z here, x, y, z. So that's the x, y, z, right? Use right hand rule, x, y, z. Okay, so we have the x. So this is the in x-axis, x-axis going up, right? X-axis. X equal to half d over 2. The boundary is located half d over 2 and negative d over 2. Waveguide. So this waveguide is extended to infinite in the y, right? In the y and the z direction, right? In in the y, and this waveguide is extended in y and the z direction. And we want to say this wave, right? Electromagnetic wave, let's assume this is propagating in the z direction. It could propagate in y, right? But let's just assume this is propagating in the z. Wave propagates in z direction, right? Wave propagates in z direction, right? And this thickness d, right? The thickness d, the thickness d is typically on the order of wavelengths lambda. So usually it's on the order of wavelengths, right? It could be half wavelengths, it could be 2 wavelengths, it could be 4 wavelengths, right? Okay, so refractive index we'll define as this is N2, N1, N1, right? So Nx, so this Nx equals, this is N2, N1, when absolute value of x is d over 2, right? And then otherwise, right? Otherwise, right? So we know that this N2 greater than N1, right? N2 greater than N1. N2 is greater than N1. It needs to be the high index in the center and the low index in the cladding, right? High index in the center and low index in the cladding, okay? Just like the optical fiber. Okay, so here we are going to use the Maxwell's equation. Maxwell's equation. Maxwell equation, curl of E plus mu partial H partial T equals 0, right? So this mu is the permittivity, right? Oops. This mu is the permeability, right? Yeah. Permeability, and then we have curve of H minus epsilon partial E partial T equals 0, and this is the permittivity. Permittivity, right? Okay. Okay, so let's have, this is the equation 1, this is the second equation, right? Let's use a curl operator on the first equation, right? Let's apply this curl operator on first equation. What we have is curl of E, right? So let's apply curl operation on the first equation. We get curl of E plus mu. Then we have partial T, right? So let's apply curl operation first. So curl of H equals 0. Okay, so then once we have this operation, we'll find curl of H. We can use the second equation, replace curl of H by epsilon partial E partial T, right? Partial E partial T. So what we have is curl of E, then plus mu epsilon, because this curl of H replaced by epsilon partial E partial T, so mu epsilon partial becomes second derivative of E equals 0, right? So meaning that I'm now replacing curl of H by partial E partial T, right? Electric field. So now I remove the H, right? Magnetic field in this equation. It's now all the E function, right? And function of E. Now let's use the identity in the this operator. Partial E, curl of E equals the divergence and the gradient of E minus this Laplacian operator, right? So this is the divergence, right? Divergence, right? So this operator is divergence, and this is the gradient, right? This is the gradient. Okay. Yes, okay. So now this is the divergence. I mark it wrong. So this term is the divergence, right? This term is the divergence. Okay, so now we have a homogeneous and isotropic medium. So we have homogeneous and isotropic medium. We have homogeneous and isotropic medium, and we know that this divergence of D equals rho equals 0. So in other words, we don't have any charge. We don't have any isolated charge in this field. And this D is epsilon E, right? D is epsilon E. So at any section, this epsilon is a uniform. It's uniform. So we will find this divergence will be 0, right? Divergence will be 0 because the divergence of D is 0 because there is no charge, right? So this charge. So this rho is charged. There is no charge, right? Let's say no charge, right? And D is epsilon E. So divergence of this E will be 0, right? Will be 0. Now this curl of E becomes this Laplacian operator, right? This Laplacian operator. So we get this Laplacian operator is Laplacian operator E. Then we substitute there. This becomes negative. So minus mu epsilon partial E partial T, second derivative. So a lot of quite some derivation. It is from electromagnetic waves, right? Quite some derivation. It is from electromagnetic waves. Feel free to interrupt me if you have questions. Let me bend it down a little bit, right? So we have more space. Okay, so now we get this equation, right? We got this equation. This equation is not general, right? It is not general. It only applying for the homogeneous and isotropic media. There is no charge, right? There is no charge. Okay. Now let's assume for this problem. For this problem, we will have monochromatic plane wave solution, right? So we have monochromatic plane wave solution. Plane wave solution, right? Monochromatic plane wave solution. We assume the wave propagates in Z direction, right? propagate in z direction. Right? Propagate in z direction. Let's assume E has harmonic waves. Let's assume E equals E naught exponential I omega t minus beta z. Right? So, so in other words, this beta is the propagation constant, right? Propagation constant, just like this K naught, right? K naught. In other words, this omega t is time harmonics, right? Time harmonics omega t. So E naught. What it means is that in z direction, how phase will be changed. So, for example, excuse me, if it propagates in z direction, how much change in the unit beta represents the rate of phase in change when it propagates in unit distance, right? Rate of change per in phase per unit length, right? That's the beta. So, for example, if I change in 1 meter, how much the phase will be changed? That's what beta represents, right? And also remember what is beta? What's the K naught double prime, right? K naught double prime is the second derivative of this beta. So that is what we learned previously, right? This is the beta. Okay, and this beta is frequency dependent, right? That caused a lot of problem in dispersion. That actually, so we spend a lot of time, right? But for now, for this problem, let's study chromatic plane wave solution. So we'll study beta just for the single frequency, right? Or single wavelengths. Okay, so this beta is propagation constant. It's called propagation constant, right? That's what we deal with a lot. Okay, so now this Laplacian operator is partial x, right? Partial x, and then second derivative plus partial y, second derivative, partial z, second derivative, right? And then let's look at this partial e, partial t, second derivative, right? If we take the second derivative, what happened here, right? So if we use the e as this form, then partial t we have I omega, right? We have I omega. So I omega 2, I omega times I omega, this is negative omega squared. So every time when we see a partial t second derivative, we're going to have negative omega squared coming out, right? Negative omega squared coming out. Again, please feel free to interrupt me. It is more helpful. We're supposed to be more interactive, right? It's supposed to be interactive learning, right? Okay, so and then this K naught, right? K naught is omega over c, which is omega, and c is defined as square root of 1 over epsilon mu, right? So this is the wave number in vacuum, right? Wave number in vacuum. So this is in a vacuum, right? So wave number in vacuum, right? And excuse me. And so in the vacuum, it is omega over c, right? Omega over c. Okay. So this is in the medium epsilon. This is the epsilon naught. In the medium will be epsilon naught times n squared, right? Refractive index. So if we have epsilon 1 and epsilon 2, we have epsilon naught, which is the permittivity in the vacuum times the refractive index. That's the refractive index square.
Dr. Who?
Yes, thank you.
Just a minute ago, you took the partial derivative with respect to t, or I guess the second partial, where you have the, yeah, right there. That was the partial derivative of e with respect to t, correct?
Oh, that's correct.
So how, could you explain how you got that? I'm a little confused about how the e naught dropped out and where the exponential went.
Okay, thank you. Thanks for your question. Let me make this. Yeah. So let's take a look at this, right? So let's take, assume you can still see it, e t squared e, right? So, so let's use this equation. So that is partial t squared and e naught exponential I omega t minus beta z, right? So in this case, do we still have room? Yeah, up to this point, right? We still have room up to this point. Yeah, so all of this, there is no t term. So E naught, there is no t term. Beta z, there is no t term. So let's just derivative, right? Take what first derivative, this will be I omega, right? So it's E naught exponential I omega t minus beta z. And then we take another derivative, right? What we have is, because this is only E t term, so we take another derivative, it's going to be I omega. So it's the I omega, have another omega, it's negative omega square, E naught exponential I omega t minus beta z, right? And that will, we stare at this piece again, we found out that is actually E, right? This is E. So in the end, it's negative omega square E. Right?
Okay, that makes sense.
So if we look at this equation again, it is the E and E. So anytime when we apply this partial t square, we have negative omega square falling down. So that's why I wrote this as partial t square equals negative omega. And I didn't put E there because it applied on H also.
Okay, thank you.
Is that good? Okay, thank you. Thanks for your question. You know, it's if we were in the classroom, it's more, you know, effective, it's more interactive, but we'll do that online. We'll try our best, right? So please feel free to ask questions. If you have questions, chances are your classmates will have similar questions. So I use this partial t as an operator, right? As an operator. Okay. Now let's look it up, right? Let's look it up, and we have partial t as this. Let's do partial z square, right? Second derivative in terms of z is that we apply this on derivative on z. We have negative I beta falling down, right? We have negative I beta falling down, so we apply second time, so it is negative beta square, right? Negative I beta times negative I beta is negative beta square, right? Okay, so then this will be a second derivative on z. Now next, we are going to apply this equation, this operator on the original equation we derived, right? We apply this equation on our original equation, right? Our original equation. What we get is that we will replace the Laplacian operator by partial x square plus partial y square. And then this time we write the E, right? This time we write this E. And let's write EXY, right? E, now I write the EXY. So this is XY distribution. It is XY distribution. And the beta t component, we write as exponential I omega t minus beta z, right? So then we will add this partial t, right? So then we have this partial t. So hold on. So that's we will have the e, right? So hold on. Yeah. So then we will have this e. So that will be good. So we will have partial. So that's this component, right? This Laplacian is this. We leave the second beta, right? So beta, let me write it down. So it is minus beta square and then EXY, right? So I have the partial x, partial y, partial z right here, minus beta square, right? Minus beta square. Now we have this term. This is the mu epsilon. So we have mu epsilon. And partial t is omega, right? And negative omega, negative, so it's plus. And then omega square, right? So we have this omega square, right? Omega square mu epsilon, right? Mu epsilon. Okay, so that's the that's what we have, and that equals 0. Right? So instead of this equation, now this equation, let me use the let me use equation 3 becomes now equation 3, right? Becomes this. Right? Equation 3 becomes this piece. This equation is coming from here, right? We use partial x, partial y, partial z become negative beta square. This is partial t, right? This is partial t, okay? Okay, now let's rewrite, right? What is this epsilon? Epsilon is epsilon naught times n squared. What is epsilon naught? Epsilon naught is the permittivity in the vacuum. What is n? N is refractive index, right? N is refractive index. And we can write this become k naught square, right? If we have k naught square, it will become omega square mu epsilon naught. So let's rewrite this equation: x squared plus partial y squared. Can you all see it? Yes. Okay, partial y squared, and then EXY, right? So this is X and Y profile. This is XY profile because the Z and omega t profile we already know. So plus this become k naught square, and then k naught, right? This become k naught square, right? And k naught square, and because k naught square is omega square mu epsilon naught, and then we have nx square, right? Minus beta square EXY equals 0. So that this piece is mu epsilon omega square. We write that as k naught square nx, right? What is k naught? K naught is omega over c, which is the wave number in the vacuum, omega over c, right? This piece. This is refractive index minus beta square, right? Okay, any questions so far? Okay, so as always, we will have some derivation, and then once we have some derivation, we will learn how we can use it, right? And from this class. Yes, questions?
Should there be, on the equation you just wrote, should those first partial x squared and partial y squared, should the numerator be squared as well in those?
Oh, yes, thank you. Thanks for pointing it out. That's absolutely correct. Thanks. So it's the second derivative. Yes, you're right. Okay, great. Thanks for pointing it out. Okay, now when we look at this equation, right, we need to actually determine two cases, right? First, if my k naught square and x square is greater than beta square, greater square, and partial y equals 0, right? In other words, now because the y direction, right, is infinite. So if my field, this is more general, right? My field takes the derivative in y direction, there is no variation. But in x direction, it has some variation, right? So the field in x must vary, right? Because my index is different, right? Index is different. But in this equation, partial y is infinite. So let's assume this partial y will be 0, right? Because the field, the table, this actually the problem, it tells us that there is no change in y direction. So partial y will be 0. So now let's just remove this term, right? Partial y will be 0. I write this equation so it's more general, but in this problem, partial y will be 0. And then let's look at this term. If this is positive, right? This is positive. So in this case, if this is positive, then what we have is let's move to the right-hand side, and the partial x is less than okay. So let's write this equation, partial x, right? Square e. Let me write this as ex, right? So now my E field is only very in x. And then we move this to the right-hand side, it's become negative k naught square n x square minus beta square ex. That's the equation we have, right? That's the equation we have. Okay. Okay. So if you look at this, this is a number, right? This is a number. So second derivative of this is a number times the function itself, right? So, but in this case, it become a negative, right? Because k naught x squared minus something is a negative coefficient, right? Because this is a negative. So now you think about it, right? So this function, second derivative of a function is a negative times something, right? Times of its function. So can you think of any function? What would be the representation of the E field? What kind of function should this E field be? So that second derivative of this function will become a negative times itself. Right? Let's think about it. So if I have x, it's a quadratic, right? X squared. Then we take a derivative of x, it becomes x, right? X. So what I want is some kind of function, some kind of fx, dfx equals to something but negative, but it's the same as fx. Can you think of what kind of fx it should be? Any idea? But there should be a negative. Oh, I need to second derivative, right? Second derivative of a function is a constant, is a negative constant times something. I should have this ax, right? This ax is something. Any idea what kind of function it is? How about sine function, right? How about sine function? Okay, let's take a sine function, right? What if I have sine ax, right? Take a first derivative, right? So this will be a, if I have sine function, then it will be cosine, right? So it will be cosine ax, right? So this will be, and then we take another derivative, d dt sine ax, then second derivative, right? Second derivative, we will take another derivative of cosine, become negative a square cosine sine ax, right? At, it should be at, this should be t, so it's the sine at, right? So the second derivative of the sine function is a negative a square times the function itself, right? Okay, so if we look at this function, then the solution will be sine, right? The solution will be sine. Alternatively, cosine function will do the same thing, right? Cosine function will do the same thing. If I have a cosine function, second derivative of cosine function is a negative some coefficient times the cosine function. So the solution is either sine or cosine, right? So solution is sine or cosine function, right? Okay, now let's see. If k naught square nx square is less than beta square, and partial y is still 0, right? If I have this, if this number is less than k beta square, then we move to the right-hand side, we'll do the same thing and move to the right-hand side. What we have is partial x squared, right? Ex equals this beta square minus k naught square nx square ex, right? So now we move to the right-hand side, it becomes beta square minus k naught double prime nx. And this becomes positive. This becomes positive. So now what we have is second derivative of x is positive times the something, right? Positive times the something. So can you think of what kind of function? Previously, it's the sine or cosine ax, right? Sine or cosine ax, because the second derivative would give us a negative. But now we want to take something, the second derivative, and it will also still be a positive coefficient times a function itself. Can you think of what function could be ex? Any idea? How about exponential, right? How about exponential? So the solution is exponential function, right? For example, let's just think about it, right? So exponential 5x. Let's take a derivative of it become 5 exponential 5x, right? Let's take another derivative, d dx square exponential 5x equals 25 exponential 5x. Right? So this will be 25, this could be 25. So the second derivative of its function is that if the function itself times a coefficient, this function could be exponential, right? But if I want to be a negative, it won't work, right? For example, if I have a -5 here, then this becomes -5, but we add another -5, this becomes +25, right? So exponential will not give me a negative sign here, but sine and cosine will give us a negative sign, right? So depending on whether the k0 square and x, which one is bigger, whether it's k0 square and x is bigger or beta square is bigger, our solution could be sine, cosine, or exponential. Questions? Okay, so now let's look at this, right? Those will be our solution. So now let's look at this solution. So it's called guided transverse electric mode. So it's guided transverse electric mode. It's the TE mode, right? Called guided transverse electric mode. It's the EY equals EY. So this is we have the EY component varied by X, Z, and the T, right? The EY meaning that the field is the Y direction. The field is in Y direction. Is EM equals to EMX. MX exponential, right? Exponential I omega T minus beta Z, right? So in other words, this is harmonic at the time and propagating in Z. Field is varied by X, right? So we have some kind of field variation in X direction, but the field is oriented in Y, right? Field is oriented in Y. So let's see the EMX, right? We will expand it out when X absolute value is less than D over 2, is less than D over 2. Excuse me. So we know that this N is bigger, right? N is bigger. N is going to be larger than the propagation constant. When X is greater than the D at the outside, so this N, this K naught X going to be smaller, So in this case, in the center, it's going to be sine and cosine, and outside it's going to be exponential, right? So it's exponential decay at the outside, but in between, in the middle, it will be sine and cosine because in the middle, N refractive index is bigger. So let's write it down. It's A sine, right? HX plus B cosine HX, right? So let me write it. X is less than X absolute value is less than D over 2, right? So in between, it's the combination of A sine HX, B cosine HX, and X is less than D over 2. we will determine the h later on. And then in the outside, when x is greater than equal to d over 2, when x is greater than equal to d over 2, we need to have c exponential negative qx, right? So in other words, it should be exponential, but our solution needs to be decayed, right? Otherwise, we have non-solution. It is exponential, but it needs to be exponential decay. Otherwise, we don't have a solution. So we add a negative sign here. Q is positive, assuming Q is positive. So C exponential negative QX. Then we have this D, right? We have D also exponential. This is also the Q, but this time let's use the Q, positive Q, right? Positive Q. So the reason is that x is going to be less than equal to negative d over 2. So in the negative axis, we have exponential qx because x is going to be a negative number. So the whole thing is going to be decay at infinite, right? The whole thing is going to be decay at infinite, right? So now the last thing is what is h and what is q, right? What is h and what is q? So let's look at the h, right? So in other words, if we substitute em into the original equation, right? So then this will be the, if we substitute a sine hx there, so this become the excuse me. So partial x ex second derivative is going to be negative h squared ex, right? So if we have this either sine or cosine, second derivative of this e field is going to be negative h squared times ex for either ex or for either sine or cosine h, right? So now that means h should be this piece, right? So h should be square root of k naught square and x minus beta square, right? Okay, so that's the first for the h. And then for the exponential, right? For this exponential. And then we have the exponential. This is the first case when x absolute value is less than d over 2, where x exponential value greater than equal to d over 2, then my partial x squared ex, right, is going to be negative, either negative q or q, but we take second derivative, it's going to be q squared ex, right? Q squared ex. So what is q? Q is going to be square root of beta squared minus k naught squared and x squared, right? Beta squared minus k naught squared and x squared. So this is going to be the q, this is going to be the h, right? That's the representation for this slab waveguide problem, right? So I'm going to stop here. I'll leave. I'm going to stop here. I'll leave the time for the lab session. But for today's class, we use the Maxwell equation. We use Maxwell's equation, derive this wave equation, right? Wave equation. Once we have this equation determined based on the k naught double prime and beta, which one is bigger, we have sine or cosine solution or exponential, right? So in this case, we will have whatever solution is, and then we have decay and whatever solution is in the middle, but it will be decay, right? So we have exponential. We could have this increase also, right? But But if we have this solution, it will be a non-solution, right? We mathematically it's satisfied, but physically it could not be possible. So it must be decay, right? It must be decay, but in between it's sine or cosine. So we write down this form, and we have H and Q. H and Q, then this is the representation. Next class, we're going to use boundary condition in order to determine what kind of field it is. Any questions up to here? Okay, so that's it. For the rest of the class, I want to leave it for our lab session. Hopefully you already kind of spend some time and finish all of them. And but at least I want to go over your problems during the class. At least your figure problem 1 to 4 should be done. So I want to leave the rest of the class time for